what temperature it was in the eastern U.S. when I got off the airplane. I'll have to confront it when I go back. So I'm going to be telling you about your perception of ambiguous scenes, okay? So this is a very famous static ambiguous scene, two faces or a vase. And if you stare at that for continually, you will see that your interpretation switches alternately between the vase and the two faces. It's not like you choose one at the beginning and that's it. Your perception does alternate. Another example is the Necker cube. If you fixate on the green spot, your impression of which corner is closest to you is going to change, but you have to stare at the green spot. So there's some alternation in your perception of these ambiguous scenes, even though the image on your retina is constant. Okay? So there's something going on in your head. The first example I saw of this was by Richard Anderson, in which there's a glass cylinder with dots painted on it, random dots, and it's rotating. And at times you will perceive the dots going in this direction, and at other times you'll perceive the dots going in this direction. It's being projected onto a two-dimensional scene here. And of course, this is done with monkeys, so you can do electrophysiology sometimes on monkeys. It's just kind of hard to get them to tell you what they perceive, right? Okay, so this work is done in collaboration with my colleague Nava Rubin and with various postdocs and students. So the most famous paradigm for this is binocular rivalry, in which one image is presented to one eye and a different image is presented to the other eye. And you do this with red-green glasses, okay? And then you're asked to report what is your perception. Again, you don't report a mixture of the scenes that are coming to the two eyes. Sometimes you report the left eye scene, sometimes you report the right eye scene. So some of the description I'll give, I'll talk about binocular rivalry. Although most of our experiments in Nava's lab are done with yet a different stimulus. This is not a binocular stimulus, this is a monocular stimulus. So what you're going to see is two overlaid gratings of bars, and the bars are drifting. Okay? And so then sometimes you will see the bars pass through each other, transparency, or they may appear like they're drifting together, coherence. So this is bistability between coherence and transparency. The nice thing about this stimulus is that it's very easy to quantify. The velocity of the bars, the orientation of the bars, the wavelength of the bars, and so on are all parameters. Okay, so fixate on this spot. And now you see if your perception alternates between coherence and transparency. Are the bars sliding over each other, or are they going together? Okay, does somebody not see this alternation? Does somebody not perceive this?
So if you don't fixate in the center, it doesn't work.
Well, you shouldn't move your eyes around. It's a mechanical perturbation, right? You can cause a switch by that kind of thing.
It's not by stabilizing. I can sometimes see multiple.
Okay, so I'll give you some other examples which are even more powerful than that. This is the same. This is the same. Okay? But now, here's some cases where we can manipulate some of the other parameters. Okay? So here the angle is changed. This one tends to favor transparency. Okay, you don't see one sliding over the other pretty much in this particular case. Okay. Did you see any alternations here? Yeah? Uh-huh. So there's this one. This one is really pretty easy to see the alternations. I just changed the velocity and the wavelength. And sometimes you can see, I don't know if you see between the alternations, you can see coherence. Briefly. So this is an example of one that's tristable. Okay, and it seems to me that there's always a coherent state between the switches. Okay, what is the percept that you're seeing? One is sliding over the other, one is on top, and then the other one is on top. Okay, so there's a depth cue that's being alternated here. Okay, even though the image is the same, there's other kind of cues going on here. Okay, so this is sort of the schematic. Image to one eye and binocular rivalry, image to another eye. Okay, and you'll report the red perception or the green perception. And the data that we collect is the time of perceiving the red or green percept. Okay, and you'll see that the durations are random. The alternations are not perfectly periodic. So there's a statistical distribution for the distribution of durations. And so in many of these pictures, I'll tell you the mean of that distribution. Okay, so Levelt was a psychophysicist that collected some of the different properties of this perceptual bistability, this alternation, in the context of binocular rivalry. And so they have different names. Levelt's proposition 4, okay, is for perfect symmetric stimuli, say the wavelengths, or in this case, the contrast of the two images are identical. And as you increase the intensity, or say increase the contrast of the two images, the switching time decreases. There's a more frequent switching as you increase the intensity. Here's a case where you hold one of the stimuli fixed and you decrease the intensity of the other. So the green is fixed and you decrease the intensity of the red image. And when they're, of course, when they're identical intensity, the dominance time is the same for both of them. But now when you decrease red, you barely change the dominance, the mean dominance duration of the red interpretation. What you do is increase the dominance time of the green. Okay? So as you weaken red, you don't change the red dominance duration. You increase the green, which means you decrease the fraction of time that you perceive red. Okay? So that's intuitive, but the way it happens is not so intuitive. Okay? So we'll be talking about these propositions of Levelt. Okay, this is a rendition, a scaled version